All right, the half-life of plutonium, Pu, I guess that's plutonium.
Yeah, that's plutonium.
There it is, there's the rest of it. Plutonium is 24,110 years. That means in 24,110 years, you have half of what you started with.
Yeah.
10 grams of plutonium was released in the Chernobyl nuclear accident.
Yep.
How long will it take? I have no idea if that's accurate or not, by the way. How long will it take for the 10 grams to decay to 1 gram? It is estimated that 1 gram inhaled as plutonium oxide dust can give cancer to about 5,000 people.
That's really sad.
Yeah. Again, this seems like it's a researched problem, but I don't really know. So let's start with what we know.
10 cut into halves.
So at time 0, there was 10 grams of plutonium. I want to know, well,
at time 24,110, there's going to be 5 grams.
Yeah, so it never really comes out and specifies that out nice and neat, but having a half-life of 24,000 means 24,000 years will be down to 5 grams.
Which unfortunately means it doesn't go nicely down to 1 gram.
Right, yes. If it asked for when will it be 2.5 grams, you'd be like, well, I'm not even going to work the problem. I mean, I'm going to work it, but the math would be 48,220. So, but they didn't ask for that. Although we could get a pretty good idea here.
Yeah, I decided to play with it, and I was like, this should be about 81,000.
So, twice 24 is 48.
Mm-hmm.
Another 24 would be 72. But that would get us to 1. It should be a little more than 72, I think. But we'll find out for sure. Okay. Any sort of half-life or growth or decay problem, I guess we'll use P for plutonium. It means dP dt equals K times P. It's proportional to the amount that's there. The growth rate or the shrink rate, I guess. So in some sense, this is exactly like the problem we just did. Separate. That's the free point. It's supposed to be the free point. Integrate. So natural log of P equals KT plus C. E to the KT plus C equals P. So P equals C, different C, E to the KT. All right, and again, we've got 2 points. Well, I sort of stuck a third in there, but that was me just trying to guess the answer. So 2 points, 2 unknowns. We've done this enough to know when I plug in 0, 10 what I'm going to learn?
Yeah, C.
C is going to be 10.
C, we do know what we got.
So 10 equals C, E to the K times 0. So, yep, C equals 10. As expected. Our initial amount. Who knows what K is going to be, because it's going to have some wild numbers in there. But that's okay. We'll save it in the calculator. Let the calculator deal with it. So next, 5 equals 10 e to the k times 24,110. So 5 divided by 10 is 0.5. E to the 24,110k. Again, I can't get to my calculator fast enough here. Natural log 0.5 equals 24,110k.
Which means K equals that.
24,110. Whoops, got going too fast. Almost messed that up. Natural log 0.5 divided by 24,110. The Again, I'm not even going to write down what that is. I'm going to find it and save it, but it's probably going to be too ugly to worry about. Yeah, I don't want to write that down. Store that as K. So P as, whoops, we're not looking for P, we know P is 1, we're looking for time. Oh, we haven't done one quite like this today anyway. Okay, that looks weird, but we know K, right, it looks like two variables, but it's not really two variables because I know what K is. So 0.1 equals e to the kt. Natural log both sides. And again, I have to keep reminding myself, I know what K is, I know what K is, I know what K is. Stop thinking it's a variable. So T equals natural log of 0.1 over K.
And since I gave us some units.
So natural log 0.1 divided by K. 80,091 years. Again, it's supposed to be 3 decimals.
0.686.
Seems weird they would want that one to 3 decimals, but right. 80,000 years from now, do we care about 0.686 years?
I mean, depending on how many people have cancer, maybe.
I guess. Who's left at that point? So in 80,000 years, and that fits, right? We said at 70,000 years we'd be down to 1.125. So yeah, that makes sense. Again, I like the problems where they give us lots of points because I think you feel good about your answer. All right, let's do number 9. By the way, this isn't like an every year free response question, but it is every few years they put one on there, and one of the times in the recent few years it became famous among calculus circles. Be careful how I phrase that. The potato problem. Yeah, but
this is a difference between the temperature. There's a difference in there.
Yeah. So it will usually walk you through what you need to know. It's just it takes a paragraph to set this problem up. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. That's a lot to think about. Okay, so let's let T be the temperature of the object, because that's probably what we're going for here. But I'm also going to need the temperature of the medium, like the surrounding room. So I don't really want to use
T sub O, T sub N.
That works for me. Temperature of the object, temperature of the medium. Okay, all the rest of the variables we'll see if we need them. But lowercase t for time is kind of standard. Okay, rate of change in the temperature of the object. So dt object over dt is proportional to, so that means equals k times the difference between the temperature of the object and the temperature of the surrounding medium. So temperature of object minus the temperature of the medium. Suppose that a roast turkey is taken from an oven when its temperature has reached 185. I think that's an initial condition there. So I'm going to start setting up my table here. So initially the turkey is 185. It's placed on a table in a room where the temperature is 75.
So that's where you find your T total.
So what's 75?
The temperature of the medium, T sub N.
Yeah, and I don't think that's changing, at least for the purposes of this problem. It's a conservation of energy thing going on. Like as the turkey cools, the room heats up, but I don't think the room heats up enough for us to worry about the 75 changing. If the temperature of the turkey is 150 after half an hour, what is the temperature after 45 minutes? Okay, well, there's also something goofy going on here. Hour and minutes.
30.
So, I don't know which. We need to switch to
with
one or the
minutes.
other. It doesn't matter which one we switch to.
Let's go with minutes.
I think I would go minutes.
I would go minutes.
So after 30 minutes, the temperature is 150. What's the temperature after 45 minutes?
Could you just change the
Probably around 130. Yeah, probably. Hold on a second. That's kind of a joke, but that's good. To see it needs to be less than 150 for sure. If it's negative 12, then something's not right. It should probably be more than 75 because it can't cool down past the temperature of the room. So, somewhere between for sure less than 150 and for sure greater than 75. Trey guesses 130. Is that what you said? Roughly. We'll see. Who knows?
Actually, 122.
I was just wondering if you could replace T sub m with just 75 in your...
Yeah, I'm going to do that next. T sub m is not changing, so I'm just going to put 75 in there. And for that matter, I think I'm just going to switch to T, capital T, rather than T-O. Just so I don't have to write the O.
Over and over.
Okay, so this one's a little different than the others because there's an extra something going on there. Anti-DV. Heat. Separate. Integrate. What about dt over t minus 75?
We just include that in the line.
Because there's no sign change, there's no chain rule to worry about. If you need to use substitution, you would let u be t minus 75, and du would be dt, and it would all work out to be natural log of t minus 75. And I don't really need to worry about the absolute value here, because just like science says, it's not going to drop below 75.
But once you raise it to e, you can move the 75 to the other side.
E to the kt equals t minus 75. Whoops. Kt plus c. So c, e to the kt, equals t minus 75. So t equals 75 plus c e to the kt. And once again, I've got 2 points to help me solve my 2 unknowns. So the temperature is 185. Be careful, C is not 185 on this one like it was on some of those previous ones.
It's 110.
C is sort of the initial, not the initial temperature, but the initial difference, I guess. So C equals 110. So T equals 75 plus 110 e to the kt. Yeah, so if I plug in 0 for time, I get 185. And I'm guessing k is going to be negative, so that this 110 decreases. After 30 minutes, 75 plus 110 e to the k times 30. I'm solving for K. Subtract the 75. I don't know what 75 over 110 is, so I think I will just leave it.
0.681818181.
Yeah, I'm just going to leave it. It's going in my calculator in a minute anyway. So natural log of, it also reduces, but I don't care. I'm going to the calculator. So K equals natural log. This is just algebra. 75 over 110 all over 30. Let's be fun and use the fraction bar. And let's go overboard with it just because. Natural log is 75 over 110 all over 30 is whatever that is. It is negative. I like that because this is decaying. The temperature difference is decaying. So store that as K. And then I want the temperature at 45 minutes. 75 plus 110 e to the K times 45. And again, I know what K is, so that's not a... I'm just plugging things into the calculator. Plus 110 e to the 45k. Yeah. 136.929. Trey was closer on his first guess than his second, but he was in the ballpark. So again, that is one nice thing about word problems in general and these word problems in particular. You have a pretty decent idea of what your answer should be, like at least in the ballpark. And so if you get something, and if you make a mistake, the chances that you get something in the ballpark are pretty slim. You're going to end up with, 5 million or negative 12 or something, and you would hopefully realize that, wait a minute, that's not right. All right, so today's assignment is the rest of worksheet 3. So Monday was 1278. Tuesday would be the rest of them. How's that for me not figuring out how many problems there are? So, should we do... Yes. Yes, we should.
The cicada one's confusing me. I'm trying to get that.
Why don't you try number 3, because it's just like the one we just did. So it should be familiar. So try number 3. At home, that just magically appeared. You might need to hit pause and walk through that. That answer seems to make sense when you look at all the other times and temperatures. Just a little side note here, like this would be, it takes a while, like when do we use math in the real world? Like, well, this is one place, like there could be some industrial production, something that causes something to heat up really hot, and you need to know, well, how long is it before I can either touch it or you can move on to the next stage of production, because you can't paint it until it's down to 100 degrees or whatever, and so you need to know, well, how much time do I need to let it cool? Is it a day, or is it 30 minutes, or is it 71 minutes? And so, it feels like, well, that seems kind of abstract or out there, but there's places where you use calculus in the real world. There's the answer to number 6.